So thanks so much. It's a great honor for me to be here celebrating the 50th anniversary of the award of the medal to Enrico, whom I consider my mentor. I had the great fortune of arriving in Pisa just the year before he would leave for the institute. So I already heard about him from newspapers when he was awarded the Fields Medal, and I was already somewhat interested in number theory. So this was a great thing for me to try to enter in Pisa, and fortunately I arrived there just in time for attending his first year as a freshman in 76, 77. He gave a course, and this contact was brief but very intensive, at least for me, and sufficient to start contact, and which eventually I had the honor of collaborating many years later. So let me say something about the course delivered by Bombieri. Was an internal course of the Scuola Normale, and intended somewhat as a complement. And the title of the course was emblematic, mathematics. So it fit, in fact, with the attitude of Enrico Bombieri to be able to work and combine tools from extremely distant subjects. Of course, we just heard about his work in analysis, and of course, he did very important work in algebraic geometry, group theory, number theory in many different branches of number theory, from analytic number theory, transcendental number theory, Diophantine equations, and more. And the course, although elementary, was very peculiar and reflected somewhat this kind of attitude. The course touched many different things, from calculus, but also algebra, group theory, field theory, and immediately gave the young attendants some general view of his way of thinking of mathematics. So, in particular, I learned the importance of effective mathematics. This is a very vague word, but as I understand it is a general word reflecting his way of doing mathematics. But today, in this short talk, I will just touch effective from the Diophantine, strictly Diophantine, more technical sense of Diophantine equations. Effective Diophantine analysis. So it is not easy even to formulate in somewhat exact term what effective means, and I will skip this. I think there is no general consensus, not even among the experts, of what is the meaning. So let me adopt a naive meaning. In the case of the Diophantine analysis, I intend this as some method, some algorithm to find the solutions to equations polynomial equations with the restricting the variables to lie in Z, for instance, this is the most basic case, or more generally in rings of integers. So to find what does it mean? It may mean to be able to calculate with a finite algorithm all the solutions if we know that there are only finitely many ones, or just to describe in some explicit way, for instance, by means of elementary functions, their set when there are infinitely many solutions, is another meaning. Or even more basic is just to establish whether there is or not a solution. This was the very basic meaning, was the one of Hilbert and problem. Establish whether there is a solution. And of course, it is well known that this was answered in the negative. Around 1970 by Matysiewicz, after work of others, Davis, Putnam, Robinson. So there is no finite algorithm to answer such a question in this generality. This was conceptually an important result which affected also other parts of mathematics, because this study involved also the general concept of theorem and such things. So the Hilbert question was over Z, but this issue is still alive, quite alive, because even varying Z and changing Z with other rings poses questions which are nowadays still open. There is, for instance, work of Major, Rubin, and Schlappenthal. Just, I think, varying Z with Q, there is an obvious answer in one direction, but not in the other. So this is a wide, plenty open. But of course, more hope happens if we restrict the generality. For instance, if we restrict the number of variables. But already for affine equations in two variables, there is no known provable algorithm. I insist on this word provable because there are conjectural algorithms that should be, if assuming certain conjectures, certain algorithms, we will know that they are finite. So there is no provable algorithm, whereas for certain other problems, there is not even a conjecture of what could be an algorithm. So, let me say something about this. I will concentrate on this very special problem, still open in the most general case. So when the curve, if if the curve f equals 0 is genus 0, and at most 2 points at infinity, then there is an algorithm. There are algorithms. And this, everything in this case boils down to the Pell equation. So this equation goes back to ancient mathematics, and it appeared also in studies by Fermat and the English mathematicians of that time, and then Lagrange, Legendre, Gauss, and so on. And it appears in quite a number of different problems in number theory, and not only. It is important also in Matiasiewicz proof. And this equation allows, so it has always solution if delta is an integer, positive and non-square, always non-trivial solutions, so with y not 0. And this, the knowledge of effectively solving this equation enables one by a known theory to solve every equation of genus 0 with at most 2 points at infinity. So in 1909, Dewey made a kind of breakthrough because he was able to prove that similarly looking equations, I write just an example. So under the same conditions, but if D is at most 3, is at least 3, then there are only finitely many solutions. In integers, of course. So this was a breakthrough at that time because every Diophantine equation at that time, they were treated with ad hoc methods. Every equation was a problem in itself. And this was the first theorem covering families of arbitrary degree, for instance. But the Dewey's argument was conceptually ineffective. It is an interesting kind of ineffectivity, because the principle is that Dewey assumed to have some solution sufficiently large, and from that solution, he used the solution to construct certain polynomial constructions which showed that no further solution could exist. So it was basically ineffective for this reason. And so a long time had passed until in 1970, I think around 1970, Alan Baker used the transcendental theory of logarithms to make Dewey's theorem effective. This was interesting because, somewhat surprisingly, the study of transcendental numbers, which apparently are the furthest from the integers, had implications in the case of integers.
Effective means a bound?
A bound, yeah, effective bounds, yes. Actually, in terms also of elementary functions, quite large bounds, but using only iterates of exponential function. This remained the only method until Bombieri in the 80s and also later. Bombieri resurrected Thure's method. So I have said that Thure's method was conceptually ineffective because the existence of this hypothetical large solution was essential for the method to start. And hopes were very low, and because nobody knew even a single instance where such a large solution could be found to apply the method in practice. So the belief was that such a large solution, which would enable the method to work in special cases so effectively, would not even exist. So Bombieri had the strength of thinking to break down this conceptual obstacle, and somewhat well, first he introduced the use of the so-called Dyson lemma of Freeman-Dyson. This lemma was important in proofs like Thure's. And it was important because the proof of Dyson lemma involved only algebraic concepts like degree and not the magnitude of the integers which entered in the constructions. So this enabled to get out of the arguments, first getting out of the height of the solutions. So this was a first important step to use this Dyson lemma. But another important step was so to reverse the role of in the Diophantine approximation. What do we mean by this? In Thure's proof, you see, if you find the solution, for instance, to the Pell equation, solution to the Pell equation produces a very good approximation for the square root of that. And similarly, solutions of Thure's equation produce good approximation of the algebraic numbers solution of the polynomial behind the equation. So we have a fixed number and we try to approximate. In Bombieri's approach, which goes to roots, it takes very large order roots of the number to be approximated, and the role of the target and of the approximant is, so to say, reversed. So this was another crucial step which allowed, and it is a complicated theory of equivariant approximation, studying also simultaneously with conjugates. And the result was an entirely new effective proof for Thure's, but not only. Not only. The approach could treat also Diophantine inequalities. Okay. Is alpha is an algebraic number. And we want to approximate it by elements in a finitely generated group. So these GIs are given. Algebraic numbers, and the variables here are the exponents.
Billion,
Excuse me?
billion group,
Uh,
and a billion group.
Yes, a bit, yes. Yes, we just take the group generated by the GIs. They are algebraic also. And we want an inequality of this shape. Here is the so-called height of G. G is this product. So this G lies in a finitely generated group, and we want a bound of this sort, so that the approximation is so strong that the difference is less than the height raised to some negative power with a fixed k. And I may here put a V because this works for, may be done for all p-adic places, not only the usual complex value. And this kind of inequality is basic, and Bombieri's method obtained effective bounds in the form that the height of G, I won't write the exact bounds that can be obtained, but this is something less or equal something computable. It's computable in terms of alpha, V, K, and the GIs. And not so these exponents, this bound allows to bound correspondingly the exponents. This is important and gives, for instance, an easy effective proof of the finiteness of solutions of the so-called S-unit equation. This is very simple as an equation, x plus y equal 1, but x and y have to be invertible elements in some ring of integers or less integers. So one may think of the rational numbers, one may think of x and y being rational numbers with only prime factors in numerator and denominator in a prescribed finite set. So the equation, it is not at all obvious, not even that it has only finitely many solutions, but still less obvious to compute the solution. Ziegler already had used this equation, which in fact it is meaningful, especially meaningful because it represents the problem of integral points for the line deprived by 3 points. So the line -0, 1, infinity, the integral points of this variety leads to this equation. And this is an arithmetical analog of the Picard theorem that a holomorphic function, entire function, assumes all values but at most 1. Okay, now to conclude my talk. So all this stuff, so with the proofs by Baker and Bombieri, allowed to make effective.
Real effective means that you bound the height of solutions.
Yes.
Like X.
Yes.
Complete functions.
Some formula, which by the way involves only elementary functions.
Effective rational being computable in practice.
Yes.
Not feasible.
Effective but not feasible.
Yes. So anyway, at least from the conceptual viewpoint, all of this stuff leads to effectivity, effective for curves, fine curves of genus 1. So for instance, an elliptic curve minus 1 point, the integral point on such an affine curve can be computed. But already for genus 2, this is not known. Now, a curve of genus 2, I would like to make a comment. Any curve of genus 2 may be defined birationally by an equation of this shape, where the degree of f can be taken to be 6. And all curves of genus 1 are represented by such equation. But the problem of integral points does not mean if we have a curve of genus 2 and with some points at infinity, this is not necessarily the same problem of finding integer solutions of such equation, because this is a birational model, so it does not respect the integrality. So in fact, the methods of Baker and Bombieri that I have recalled allow to find the integral solutions of such an equation. But this does not mean that we may compute the integer solutions, the integer points on all curves of genus 2. Let me just write down a simple family. So take this affine curve. It depends on two parameters. Say they are non-zero. This is an affine curve. Actually, it is singular at the origin, but the singularity does not play. The singularity does not matter in the problem of integral points. And for generic values of A and B, this curve, the smooth model of this curve, has just one point at infinity. So there is the functions x and y, the coordinate functions, have only one pole. So for general A and B, no method is known, to my knowledge, for computing the integer solutions of such an equation. So this is, I think, the simplest borderline example, because for genus 1 we can. For cubics, we can, because cubics represent curves at most of genus 1. And here, just a quartic, we have a quartic, and we don't know. We don't know. So all what I conclude my...
We know it's only finitely many.
We know that there are only finitely many, yes. By Falken's theorem. There are only finitely many. Actually, by Siegel theorem. Falken's even proves that there are only finitely many rationals. Even confining to integers, we don't know how to compute the solution. And I conclude my talk just by stating, actually in very vague terms, for lack of time, a result of recent obtained collaboration with Corvaja and Lombardo. We apply this stuff of Diophantine inequalities to obtain that the following statement like this. there is a complex dense set of pairs A, B of algebraic numbers such that the above equation is effectively solvable over every number field and ring of integers. So this is the kind of statement which we can obtain. It is rather,
Set effective? Can you tell when A and B is in your set?
yes. Yes, thank you for the question. We can decide whether a given pair AB is in the set. So it is a rather somewhat strange looking statement because we have this dense set where we can prove effectivity, but we don't know how to do that generally.
But for a point that's not in the set, then you know nothing.
Then we know nothing.
I mean, it could still be that.
It could still be.
Yeah.
In fact, yes, there are algorithms conjectural algorithms which should work. They are based on Birch-Swinnerton-Dyer conjecture, and so the complexity of such algorithms, I think, would be huge in the sense that do not know if these conjectures are true. So we wouldn't even be able to estimate by elementary functions the complexity of the algorithms. So thank you very much. And
Enrico, today you have first comments on every talk. You don't have to make comments.
Well, not much is known about the structure of the sets of A and B, for which the method works. And there's a certain subset for which we can produce A and B. But in general, if you give A and B, you have no idea whether method for solving the equations.
When you said dense in ordinary complex topology.
Yeah, it's dense, but not sufficient.
Not dense enough to
very
be.
sparse, but in some sense.
Didn't Baker, I think Baker has used to say that everything should be decidable for curves, right?
Oh,
I
Effectively.
doubt it, but.
Okay. All right, so let's thank Umberto again. And